Today, we're going to unpack how a single incredibly simple shift in mathematical perspective completely transforms everything we thought we knew about abstract algebra. Honestly, if you've ever felt like linear algebra, group theory, and ring theory were just completely separate, disconnected worlds, well, we are in for a real treat today as we piece this whole puzzle together. But before we really get into the weeds, let's start with a little mystery. What on earth could a traditional vector space possibly have in common with the cyclic math of a clock, or even a set of random polynomials? On the surface, they seem to operate by entirely different rules. It's kind of like comparing a strict game of chess to interpretive dance. But what if there was a hidden architectural blueprint that perfectly described all of them at exactly the same time? Well, that unifying secret is module theory. At its absolute heart, a module basically takes the strict, super familiar rules of a vector space and beautifully relaxes them. It does this just by swapping out the field of scalars for an arbitrary ring. It's a framework that takes everything we know about scaling vectors and blows the doors wide open to a much, much broader mathematical reality. Here is the exact roadmap we're going to follow today. First, unifying abstract algebra. Second, the module blueprint. Third, mappings and isomorphisms. Fourth, free modules and tensors. And finally, number 5, the homological endgame. All right, let's dive right into part 1, unifying abstract algebra, and take a look at the module blueprint. So standard linear algebra dictates that a vector space demands its scalars come from a field. Think real or complex numbers, where clean division is always a guarantee. But by allowing our scalars to come from a ring instead, like integers or polynomials where you definitely can't always cleanly divide, we unlock a much wilder, way more versatile mathematical universe. It's actually amazing. By just tweaking that one single rule, all these disparate concepts just snap perfectly into place as special cases of modules. If your ring is a field, boom, you've got a vector space. If your ring is the integers, you're looking at an abelian group. If you're working within the ring itself, you get ideals. And if your ring happens to be a set of polynomials, you get linear operators. Literally every result you know in linear algebra suddenly becomes just a highly specific special case of module theory. Let's ground this with a concrete example, shall we? If we look at the clock math of the integers modulo 6, we can absolutely treat it as a module over the regular integers. And when we do that, its submodules, the sets that are closed under addition and scalar multiplication, are simply its subgroups. So that's the trivial 0, the modulo 3 subgroup, the modulo 2 subgroup, and the whole set itself. It perfectly proves that abelian group theory is really just one chapter in the larger module playbook. Moving right along to section 2, mappings and isomorphisms, where we'll be factoring out the old. Just like we do with standard groups or vector spaces, we can take a submodule and map it down into what's known as a quotient module. Basically, you take your overarching module M and you divide out a submodule N. This creates a really powerful, simplified new structure of cosets that incredibly still respects our ring's scalar multiplication. We are effectively hiding the noise to see the bigger structural picture. Now, what's really fascinating here is how the 3 famous isomorphism theorems from group theory completely, seamlessly adapt to modules. Take the first isomorphism theorem, for example. If you map one module to another, the original module factored by the kernel of that map is perfectly isomorphic to the image. These theorems are a huge deal. They give us the heavy machinery to navigate super deep mathematical abstractions just by comparing structures, all without ever getting bogged down in endless equation solving. Okay, section 3, free modules and tensors. Let's talk about measuring complexity. As we push further into all this, a pretty major structural problem rears its head. Just how complicated can a module actually get? Because rings are so much less restrictive than fields. Remember, they lack that guaranteed division. Modules can behave pretty chaotically. They can have elements that loop back on themselves, or they might completely lack a clean set of basis vectors. So, to tame that chaos, mathematicians gave us the free module. These are the well-behaved ones. They're the closest thing you'll get to a standard vector space because they actually possess a basis. Every single element inside a free module can be expressed in exactly one way as a finite linear combination of basis elements. No weird loops, no structural quirks, no rogue elements doing backflips. In fact, one of the grandest theorems of this whole framework states that literally every module is just a quotient of a free module. But what happens if we want to multiply 2 completely different modules together? For that, we use the incredibly powerful, if initially somewhat mind-bending, tensor product. The fundamental genius of the tensor product is that it takes complicated bilinear relationships where you've got two variables interacting across two modules and miraculously flattens them into a single, clean linear space. To put that into perspective, let's look at what happens if we tensor two simple cyclic modules, the integers mod 2 and the integers mod 3. Walking through the math, we're effectively factoring the mod 2 group by multiples of 3. But here's the catch. Because 2 and 3 share no common factors, meaning they're coprime, absolutely no non-trivial element can survive the defining relations of both groups at the same time. The result? The entire structure collapses entirely to zero. It is a fantastic demonstration of how the tensor product forces mathematical compatibility. Which brings us to our final act, section 4, the homological endgame: projective, injective, and flat. The absolute gold standard for measuring module relationships in advanced algebra is the short exact sequence. It is a highly precise chain of mappings where the image of one step perfectly equals the kernel of the next. It encodes structural data flawlessly, basically saying that the middle module, B, is a perfect mathematical extension of C by A. Depending on exactly how a particular module interacts with these short exact sequences, it falls into a sort of trinity of specialized classes. First, we have projective modules. These are the ones that can lift maps from a quotient back up to the original overarching module. Second, injective modules. These do the exact reverse, easily extending a map from a tiny submodule to the entire structure. And finally, flat modules. These are the incredibly useful ones that perfectly preserve exact sequences when you multiply them using a tensor product. So the absolutely crucial takeaway here is this hierarchy. As a general rule, being free guarantees you are projective, and being projective guarantees you are flat. But, and this is a big but, the reverse is absolutely not true, unless you are operating over a strict field. Over a field, everything just collapses neatly. Free equals projective equals flat. But over a ring, like the regular integers, things get wildly interesting. Over the integers, the rational numbers are flat for sure, but they are absolutely not projective. The structure totally dictates the rules. As our source material beautifully puts it, module theory isn't just some arbitrary collection of algebraic theorems. It is a cohesive, breathing web of ideas. By taking the familiar concept of a vector space and just slightly tweaking its foundation, mathematicians built a unified framework that naturally structures everything from basic group theory to complex linear operators. So, now that we've unlocked the mystery of the module together and seen firsthand how a simple shift in scalars can completely rewrite the rules of abstraction, I want to leave you with this question. How will you use this profound architectural shift to explore the very frontier of mathematical discovery? Because in modern math, module theory isn't the end of the road. It's exactly where the real journey begins.